J1 elastic collisions, part 1. So in this case, we're going to look at before. We have a mass 1 traveling to the right with velocity u1, and we have a mass 2 sitting there at rest. And this direction is positive to the right. Then if we look at the after situation, some kind of collision is going to hit this other one. The general situation is that M1 here will be going with some velocity V1, and now M2 has some velocity V2. All right, so the velocities before are designated by U, and the velocities afterwards by V, the V's. So the first thing we're going to have here is conservation of momentum. We can always write that equation down. It's conservation of momentum. And that's going to be here M1 U1 plus M2 times U2, which is 0. And that's going to equal M1 V1 plus M2 V2. The next is conservation of kinetic energy, since our situation is elastic. Then we have 1/2 M1 U1 squared plus 0, since the second one is at rest, and that's equal to 1/2 here M1 V1 squared plus 1/2 M2 V2 squared. And what are we interested in? Well, we're interested in V1 and V2. We want to know what the speeds are afterwards in terms of the before. So you can think of U1, U2, and M1 and M2 is given. So you can imagine this collision taking place in outer space. Perfectly one-dimensional problem. But we'll apply this on Earth, like we have ice skaters, or we have, say, a pool ball situation on the pool table, where the gravity is going to be pointing down is perpendicular to the direction of motion, so there's no work. There's no work. You don't have to worry about kinetic energy getting messed up if you're moving horizontally. So we'll have lots of applications here to sports, for example. So we have these two equations, and I'm going to write this pair like my friend in grad school did, with little brackets. And the first equation is M1 U1 is equal to M1 V1 plus M2 V2. And the second one I'm going to multiply through by 2. So I have M1 U1 squared is M1 V1 squared plus M2 V2 squared. There's the pair of my equation. I have two equations with two unknowns. So I'm going to be able to solve for V1 and V2. So what I would like to do next is get the parameters with the 1 on the left-hand side of the equation. So I'm going to go here M1 U1 and subtract M1 V1. So that'll be on the left-hand side like this. we're subtracting m1 v1, so the m1's in common to both of those. And then here we'll subtract the m1 v1 squared. So m1 is in common to both of those, so we have u1 squared minus v1 squared, and that's going to be equal to m2 v2 squared. So here are two equations. Now we're going to use the trick that when we have a squared minus b squared, that we can write that as a plus b times a minus b. So that means the second equation we can do something with. So we'll go ahead and write down the first equation here, unchanged. And then for the second equation, we're going to have m1, we're going to have u1 plus v1, and then u1 minus v1, and that's going to equal m2 v2 squared. Now, if we look at this equation, the pair of equations, we can see that we have an m1 here, we have this factor in common, we have the m2, we have an extra v2 here factor, an extra v2, and here we have an extra factor, u1 plus v1, so these must be equal because the m1s are accounted for. The subtraction here, the difference, and m2, and just think of this as v2 times v2, so there's the extra v2, and with this factor. So we get this equation, which is a nice equation that pops out of here pretty easily. And if I write this as u1 is v2 minus v1, like this has some profound significance because this is the velocity of approach. And here, the second mass speed minus the first one is a velocity of separation. So this is separation. So we're finding a rule here that the velocity of approach in an elastic collision is equal to the velocity of separation. That's quite cool. So now what we want to do is eliminate v2 to solve for v1, and if we have this v2 equation here, we could put in for here v2, what this is, and then we can solve for v1. So let's do that. So we have m1 u1 minus v1, that's the left-hand side here, is equal to m2, that's that m2, and then the v2 is going to be this, u1, and I'm going to go ahead and write it out as two pieces. So it's m2 times u1 and m2 times v1. And then over here, let's write these out as two parts. And what I want to do here is get the v1 by itself on one side of the equation. So we'll do that by bringing the v1 to the right and bring this one to the left. So if we come over here to the left with this piece, we subtract. And if we bring this over to the right, we're going to add. Okay, so here we have m1 minus m2 times u1, and here we have m1 plus m2 times v1. So now we have it. We have our equation here. This is kind of a cool equation. We have v1 is equal to the difference over the sum times the u1. Nice equation. All we had to do is divide by the sum of the masses. We have this as the numerator here and the sum of the masses in the denominator. So that's it, that's the answer. So we would like to then use this equation in here, which is a very simple equation that has then the V2 in it, so we can see what the V2 is. So if we do that, we find that V2, looking at this equation here, V2 is going to be U1 plus V1. U1 plus V1 by simply bringing the V1 on the left-hand side of the equation there. Then we write down V2 is equal to the sum. Then we're going to take this and plug that in for the V1. So that gets us V2 is U1. Now there's a U1 here and there's a U1 there. So that's going to be 1 plus all this in here, M1 minus M2 over M1 plus M2. That's it. So if we find the common denominator here, M1 plus M2, M1 plus M2, and there'll be then plus M1 minus M2, you can see that the mass 2, M2s cancel out, and you're going to get down in here 2 M1 over the sum. So the equation, when you put the U1 in there for V2, you're going to get then 2 M1 over M1 plus M2. And all that's going to be hitting the U1. That's it. They're the two equations. So let's check some cases. And the first case we're going to check here, I'm going to call pool or billiards. Because in pool, we're going to take here, a pool ball. It's going to be hit. A cue is going to be, hit moving this way. And we'll take these masses to be the same, the pool ball masses. And if they're the same, say this one's here at rest, and here the cue ball's on its way, to hit it, then you have, in this situation, you can apply that's our problem. Our problem is that the second mass has to be at rest. So we do have this situation, but our specific case is that the masses are going to be equal. Now, if the masses are equal, this equation here says V1 is 0. In other words, this ball will just stop. Since the masses are equal, you subtract them, you get 0. Then down here, since the masses are equal, you'll find that you get 2m over 2m. In other words, this ball takes off with the same speed as the cue ball. So first ball stops, second ball takes off.
一颗球没做好，没处理好，就会造成后面的球打起来会格外的辛苦。然后刚刚这个6做7也稍微力量不够，这球选择了下第一杆打进就有了不用刻意做球，对，没问题。
Now the second case I want to consider is baseball when here you toss the ball up so it's not moving to the left or right, and then you hit it with the bat. So the bat is going to hit the ball. So this ball is at rest, but the situation here is that the bat, the first mass, is a lot greater than the ball. So just like toss the ball out, so the ball is basically at rest with respect to horizontal movement, and then you hit the ball with the bat. So in that particular case, if the first mass is very, very massive, you can like throw away the M2s, just like M1 over M1. So that means that the bat will keep moving at the same speed. Here, the ball, since you can throw away the M2, since the ball's like, you can neglect it compared to the mass of the bat, then you have 2M1 over M1 is 2. So in other words, the ball will go off at twice the velocity of the bat. Now that's not intuitively obvious, but I would like to reserve at the end of today's little class on this section, I'm going to show you that that's the correct answer intuitively. So the next case, 3, I'm going to call tennis, and this is the case where you meet a ball. So in other words, in this case, the ball is going to hit the tennis racket. Let's draw a little picture. So here's the tennis ball coming like this, and then like here's the racket. So the second mass is going to be the big one. It's the reverse of what we had here. Here we had the first mass was the big one. So here the second mass is the big one. So the ball's coming toward the tennis racket. And here, if M2 is very large, you can throw away M1. And this is going to be, V1 is going to be a negative. If you throw this away, that's going to be a negative U1. So in other words, V1 is negative U1. And it's basically saying the mass will just, the ball will hit there, just go back the other way. Same speed. It's like a reflection. And then for the tennis racket, we don't expect that to move. So let's see, if M2 is very, very large, you have then M1 over a very, very big number, it's going to go to 0. So that checks out. That's correct. And in the book, we have the 3 pictures here. Playing pool, billiards, and baseball. Although in this case, the ball is not being thrown up in the air, it's actually coming in, and we'll reserve that to the next section where we have the motion of both masses, M1 and M2. And here, the ball's going to come, meet that tennis racket, and then just like reflect back the other way, the 3 cases. Well, let me show you this cool idea as to why the baseball, when you basically have the ball and you hit it real hard like this, that this is going to go off with twice the speed of the bat. So the bat's, U1, that's before, and then U2 here is 0. And then afterwards, the bat still moves at U1, so massive, and the U2 goes flying off at twice U1. Now here's a way to think about this. We're going to do this by a transformation of reference frames. We're going to consider, for example, what happens before on the ball field. If you're on the ball field, this is what happens. In other words, the bat is moving with some initial speed here. This is the bat speed, and we'll just call that U. And then the ball, the speed of the ball, which is here U2, this is 0. So the ball has speed 0. Now let's do the same analysis in the frame of the bat. We're riding on the bat. We are like superhero here. We can get in the bat frame, and we can call that the prime frame. We'll use primes for that. So if we're moving with the bat, the speed of the bat with respect to us is 0, because like we're moving with it. We don't see the bat moving, like we're moving with it. And then here, the speed of the ball, well, we see the ball coming toward us. That's minus u. Ball's coming toward us. So if you're moving with this bat, here, on this case, we're moving with this bat, then the ball appears to come toward us. Now, how do we get from here to here? It's very simple. We simply subtract u. If we subtract u from the bat speed, we get 0. If you subtract u from the ball speed, you get u. So here, you subtract u. Suppose I want to go this way. Well, then you would add u. If I add u to the bat, I get the bat speed. If I add u to the minus u, I get 0, see? So that's the transformation. So what happens afterwards? Well, what happens afterwards, if we're riding the bat, then the speed of the bat is still 0 because we're going with the bat. And then here, what we're going to see with the ball, guess what? The ball simply reflects, because if we're the bat, moving with the bat, we're like a wall. And the ball's coming to the wall, it's just going to bounce off, like the tennis racket case. The tennis racket case, you know, where the thing it's meeting against is very, very, very massive. So this is going to simply just go back the other way. So the ball's coming in. Here's like a wall. The ball's coming in. It's going to reflect. But then if I want to get back to the ball field, remember what the trick is. I have to add u. So if I do that, then in the ball field case, the bat still goes at u, going with the bat. And here's where the trick is. Say the ball, it's going to be u plus u. It's 2u. The ball goes at 2u. That's amazing. Think about that. It's a little bit tricky. You can think of the ball that's, you know, you can think of a ball that's being hit by a wall. The wall's coming to the ball. So here, what's that speed going to be? Well, think of you moving with the wall, then the ball's coming toward you. It's coming toward you with minus u, and it's just going to reflect with u. But remember our transformation rules, you add and subtract u. If you look at this transformation, it's very, very easy then to get the 2u by simply adding the u to get back. So to follow through in a quick little summary, you have a wall that's stationary and a ball that's stationary, and to start our problem, we're going to have the wall move toward the ball. So when the wall moves toward the ball, you have here the wall is traveling at velocity u, and the ball is at rest. Then, if you're in the frame of reference of the wall, you see the ball coming toward you. So 0 for the wall and minus u for the ball. And remember the trick to go from, this is the frame we said of the ball field, or this is the frame of looking at the room or the ball field where the wall is actually moving in the room. And then here we're with the wall or with the bat. So we're at rest and the ball's coming toward us. So how do you go from the frame of reference of the field or the room to moving with the bat or the wall? You simply subtract u. U becomes 0, and then this rest becomes minus u. Then, if you're moving with the wall, like this, then the wall's still stationary, but the ball just bounces back. It's like coming against a brick wall. All right, you're just going to bounce back with a plus u, and the wall's still at 0. But remember, to go from this frame to our first frame up here, we need to add u. Remember, 0 plus u to get u, minus u plus u to get 0. So here, if we add the u to the 0, the wall here, or the bat, is still moving unimpeded since it's so massive. And then when you add u to the ball, u plus u, you get 2u. And that's the result. Fascinating. Transformation of reference frames reminds me of Einstein, frames of reference, and had to transform from one to another.